Just remember that your next homework is due on Monday. So I think the syllabus originally said today, but it's not due until Monday. We should be finishing up Chapter 5 today. We'll start Chapter 6 on Monday. I don't think I have any announcements. You guys have any questions, comments before we get started? No. I do still have old homeworks and exams up here. If you haven't gotten yours back yet, come see me after class. Yeah. Okay. Well, let's go ahead and jump right in without further ado. So, picking up from our discussion on Wednesday, here we are on the well, I guess it's a little bit of review. We'll eventually start on the middle of page 13 there. But just remember, on Wednesday we looked at this idea of a random sample. So we have x1, x2, xn, all the way up to xn. All that they're all independent and they all are identically distributed. That's the IID or random sample. That's the same thing. So. So if I say IID or random sample, that's the same thing there. So the thing that we looked at on Wednesday was if I have this random sample from whatever the distribution is, such that the mean of the distribution of the xi is mu and the variance is sigma squared. So so here we have the expected value of each of the xi's is the same. It's mu. And the variance of the xi is sigma squared. Then if I take some statistics that I will commonly use, the sample mean, this x bar is the sample mean, or the sample average. It's going to have the same expected value, so expected value of the xi is mu, the expected value of x bar will also be mu. And then the variance is slightly different. I take the variance of the individual observations and divide that by n. So sigma squared over n. And then standard deviation is as always just the square root of the variance. So there you have it. If I'm instead looking at just the sum, so I'm not taking the average, I'm just adding them all up. The expectation of that thing of t will be n times the mean. That kind of makes sense. I'm adding up n things that all have the same expected value. I can just add up the mean n times as well. And the variance, slightly different property there, is also now n times sigma squared, and corresponding standard deviation there. But at this point, I just wanted to make this distinction clear that at this point we don't know what the distribution of these things are. Remember the xi, x1, x2 up to xn can be from any distribution. It can be from something that's really skewed or something that looks really weird. It doesn't matter. These properties are always going to hold, but I don't know what the distribution of x bar or t is at this point. The next thing we looked at was, so now let's take the same setup, except now the random sample I have is from a normal distribution. So this is top of page 13, I guess now. So same setup. They have mean mu, variance sigma squared, but again, each individual thing has a normal distribution. Then these two things are the same. Same as on the previous slide, so that doesn't change at all. But I do have this. Now I do know what the distribution of the sample mean is, and the sum of all those things are. So same properties with the expectation and variance, but now if I start with a normal distribution, I know exactly what the distribution of the sample mean and the sum of all those observations are. It's going to be a normal distribution with the mean and variance that is listed above there. So this is a very, very important result, and what we looked at on Wednesday was, because we know what the distribution of the sample mean is, we can do probability calculations just like we did before, right? So if I want to know the probability that the sample mean is between two numbers a and b, I can standardize and get down to using the standard normal distribution, and then I can use the table, or you can use your calculator or whatever you want to at that point to figure out what this probability is. So key result here is if my random sample comes from a normal distribution, I have a normal distribution down here for my sample mean and t the sum of all those things. Okay, so wanted to make a quick note here. Again, yes, we can find probabilities involving the sample mean by standardizing just like we did before. But now we want to make sure to divide by the standard deviation. That's the correct standard deviation. So before z was x minus mu over sigma, and on the previous slide it's now x bar minus mu divided by sigma over the square root of n. But just wanted to make the point that this is sort of a general form. So z is going to equal, we'll call this R value. So either that's an individual observation or it's the mean or whatever. We subtract off its mean, and then we divide by the appropriate standard deviation. So kind of this is a good general form to keep in mind. We'll take whatever random variable we're looking at, subtract off its mean, and divide by the appropriate standard deviation. So as you can see just above there, if I'm just looking at an individual observation, that's x minus mu over sigma, because sigma is its standard deviation. If I'm talking about x bar over there instead, subtract off its mean, which is mu, but then I divide by sigma over the square root of n, which is its standard deviation. So this is something that we'll see a lot in the coming chapters of this class. Just kind of to point out, this is a general form here. Okay, so but now getting on to some new material here, middle of page 13. That's all great, right? The results that we just saw are fine, but you might be asking yourself, what if my original sample is not from a normal population? So what happens if I have a random sample that's not from a normal population? So like I said before, we don't know what the distribution of x bar is, so what can we do? How can you answer questions like this? And this leads us to sort of one of the larger theoretical results we'll see in this class. We're not going to prove it. But called the central limit theorem. Has anybody heard of the central limit theorem before? A few of you guys, if you've taken stats before, probably. So this thing says, kind of, here's what it says. If we start with the same setup, we have a random sample with mean mu and variance sigma squared. So that's the same setup as we've had before. Then if n is sufficiently large, our sample mean is going to have approximately a normal distribution with the mean and variance that you would expect. So mean mu, variance sigma squared over n. And same thing for t, same thing for the sum. And then the larger the value of n, the better the approximation. So kind of in other words, if you have a random sample from any distribution, doesn't matter what distribution that is, with mean and variance, so you can always calculate the mean and the variance for any random variable, right? We've done that before. So if you have a random sample from any distribution, then the sample mean will have approximately a normal distribution with the mean and variance that you would expect it to have. And just to note that this kind of funky looking symbol means is approximately distributed as. So without the dot, it means is distributed as, and now with the dot, it's sort of approximately distributed as. So this is a very, very powerful result that we'll use to great extent in this class. So the caveat, I guess I've highlighted it in blue here, is if n is large, if n is sufficiently large. So what constitutes a sufficiently large value for n? Does anybody have any ideas what they think would be sufficiently large? What's that? 50. We have a 50. Any other ideas? 80, 30. You guys don't want anything too large? Any other comments? Any other guesses? 200. Well, it is, I guess, what constitute a sufficiently large value? Well, I'll tell you that it depends. So it depends on what the original distribution looks like. For the purpose of this class, we will use, let's have n be at least 30. So 0. So excellent. Someone's either been guessing well or reading the book. Probably a guess, right? Okay, so what we'll use for the purpose of this class, what we'll call sufficiently large, is n greater than or equal to 30. In almost any case, that will be plenty big for this approximation to be good. That's sort of the rule of thumb. So as long as n is bigger than or equal to 30, we can use the central limit theorem, the CLT. Okay. Let's try an example of applying this thing and see how this works. Okay, so here we have 40 students in a elementary statistics class. So on the basis of years of experience, let's say the instructor knows that the time it takes to grade a randomly chosen first examination paper is a random variable that has expected value 6 minutes and standard deviation of 6 minutes. Okay, so we have 40 students here, and we want to see something about how long it takes to grade all of their papers. Okay, so first question here: if the grading times are independent, so let's make an assumption that the time it takes to grade each paper is independent of the others, and the instructor begins grading at 6:50 p.m. and grades continuously. What is approximately the probability that he is done grading before the 11 o'clock news begin? So everyone loves watching the 11 o'clock news, right? Okay, so let's set up some notation here. Let's let x1, x2, all the way up to x40. So these are the grade times for each student. So that's our random variable here, and so we're told that they're independent and they all have the same distribution. This is kind of what we'll assume here. So the xi are IID. They're a random sample with mean 6 and standard deviation 6. That's what was given to us on the previous slide, I guess. And we want to know something about the total grade time, right? So that we want to know something about the total grade time for all 40 of these papers. So that's we can just add all those up. That'll be T, which is the sum from 1 to 40 of the xi, which is the total grading time Okay. So we want to know what do we want to know about t? We want the probability that t is less than something, right? So we want to make sure that he's done in, if we go from 7 to 11 and add 10 minutes, that's 250 minutes. So we want to make sure he's done before 4 hours and 10 minutes go by, which is 250 minutes. Okay, so notice at this point I haven't said anything about what the distribution of the x1, x2 up to x40 are. I've only told you what their mean and standard deviation is. So if I had told you that they were all normal, then we could use the results from before and say, oh, I know exactly what the distribution of t is, and we can forge on ahead there. But since I haven't told you that, you can't immediately jump to that step. We need to hope that we can use the central limit theorem, and if not, then we can sort of don't have anything to do here. So, but thankfully, so we can say because, so here n equals 40, that's bigger than 30 on most days anyway. We can use the central limit theorem. So what that tells us is that, kind of jumping back to what the central limit theorem says. So this says t is approximately has a normal distribution with mean n times mu and variance n times sigma squared. So because the sample size is big enough, then we know that t is approximately distributed as a normal random variable with mean n times mu, 40 times 6, and standard deviation 40 times the variance. So 6 squared is the variance. Or normal 240 and variance 1,440. Okay, so because my sample size is large enough, I can say that t has approximately a normal distribution there. Question? No?
I thought you said the variance was the standard deviation squared divided by.
Okay, yeah. So what I didn't write here, I didn't write this down. So what we can say here is that, so that's if we're talking about the sample mean, the average, the sample average, yeah. And t here we're talking about t, which is the sum, from I equals 1 to n the xi. It's approximately distributed as normal with mean n times mu and variance n times sigma squared. Sorry, I should have put that down there previously. Okay. So now because we have made this approximation, we can standardize. So the probability that t is less than or equal to 250, I can subtract off the mean and divide by the standard deviation. So this is t minus the mean, which is 240, divided by its standard deviation, which is square root of 1440. And I can see that's less than 250 minus 240. Okay, and then because of the approximation, I can say this is approximately equal to the probability that a standard normal random variable, so t minus 240 divided by the square root of 1440 is going to be approximately distributed as a standard normal, is less than, if I do that calculation, this will be 0.26. Okay, so now I'm back to the standard normal random variable. I can just go to the table, look up 0.26, and see that this probability is 0.6026. So I'm skipping that step again. I'll show you an example. We'll go back to that again to remind you how to do that. Okay, so again, the setup here, I haven't said anything about the distribution of my individual grade times. I haven't told you that they're normal or anything like that. But because my sample size is large enough, I can still use this approximation, kind of use the standard procedure there. Is that okay? Is everyone on board? Okay. Let's do this one more time. Oh, there was some more space. So let's say the sports report begins at 11:10. What's probably that he misses part of the report if he waits until grading is done before turning on the TV. So again, this is probably that the sum of all the grading times takes more than 4 hours and 20 minutes. So that's 260 minutes. This is and again, I can standardize and say that this is take t minus its mean, divide by the standard deviation. Do the same thing for the 260. And then again, because we have the central limit theorem going on here, this is approximately the probability that a standard normal is bigger than 0.53. and that's 1 minus 0.7019 or 0.2981. Yeah. So similar calculations as we just did, just kind of showing you one more time there. And this approximation is because of the central limit theorem. Okay, everybody all right there, what we're doing here? Okay, let's do another example here. Look at the sample mean instead of x bar instead of t. So let's say now the time in minutes spent on hold for a customer calling a help center is exponentially distributed with parameter lambda equals 0.2. So we're going to suppose that the hold times are independent for each customer and that we record the hold times for 35 customers here. So sort of our setup here, we have independent observations and they all have the same distribution. So we have our observations x1, x2, all the way up to looking at 35 customers. These things are all IID exponential parameter 0.2. Okay, so on the next, so what we're asking, we want to know the probability that the average hold, something about the average hold time. So we'll need to know what the expected value and variance of each one of these random variables is. Do you guys remember what the expected value of an exponential distribution is? In terms of lambda is fine.
1 over lambda.
1 over lambda, exactly. So 1 over lambda here, 1 over 0.2. 5. Very good. What about the variance? Anybody remember that?
1 over lambda squared.
1 over lambda squared. Thank you, Kevin. 1 over lambda squared. 1 over 0.2 squared, which is 25. Okay, so this is my mean, this is mu, and this is my variance sigma squared. Okay. Okay, so we want to know, again, the question we want to know here is what's the probability that the average hold time will be less than 4 minutes? So for these 35 customers, what's the average hold time? Is it less than 4 minutes? So again, let's let x bar equal the average hold time for these 35 customers. And we want to know, again, the probability that x bar is less than 4. We want the probability that the average hold time is less than 4. Okay, so again, I don't know what the distribution of x bar here is, but here n equals 35, which again is bigger than or equal to 30. So we can use this. We can use the central limit theorem. And that tells us that x bar will approximately be distributed as a normal random variable with mean mu and variance sigma squared over n. So therefore, x bar is approximately distributed as a normal with mean mu, which is 5, and variance 25 over 35. Approximately distributed. Sorry about that. Okay, so now we're off to the races as usual. We can standardize again. X bar minus 5 over the square root of 25 divided by 35 less than 4. Do the same thing, minus 5. And then because of the central limit theorem, this is approximately equal to probably that a standard normal random variable is less than negative 1.18. So now at this point you would go to the table, you'd look up the negative 1.1 row, find the 0.08 column, and that'll give you 0.1190. Okay, everyone okay with this? Questions, comments? Getting monotonous? Hopefully not. Okay, so suppose that instead of looking at 35 people, now we have 50 people. Let's try to think conceptually, what would the probability of the average hold time being less than 4, would that be less than, greater than, or the same as the one we just calculated? So I'm going to ask the same probability question. So I want to know the probability that x bar is less than 4, but now x bar is the average of 50 customers. Okay, so will that probability down here be less than, greater than, or the same as the one calculated in part A? Would anyone like to volunteer? They think it's going to be less than it was before? Okay, a few hands. How many think it's going to be greater than it was before? A hand or two. Anybody think it's going to be exactly the same as? Same as? Okay. Well, let's think about this here. So, so now with the expected, so we said the same random sample, the xi's are still IID exponential 0.2, so their expected value is the same. The mu is still 5, and the variance of xi is still 25. And the sample size is still bigger than 35, right? So n, if we have 50, this is still bigger than 30. So we can still use the CLT. So we can still use the CLT to say that x bar is approximately distributed as normal with mean mu and variance sigma squared over n, which is normal with mean 5, and the variance is now 25 divided by 50. Okay, so now the variance is 25 over 50. On the previous slide we had a variance of 25 over 35. So the variance is now what? Bigger or smaller? It was 25 over 35, now it's 25 over 50. Now the variance is smaller, exactly right. So that means I have some space over here. Trying to draw a picture. So that means if we have a normal distribution, before it was something like this, and now the variance is now smaller. So that means the distribution is going to be more squeezed together, right? So that means the distribution now looks something like that, right? And so we want to know if this is the mean at 5. We want to know something about the probability being less than 4. So the first question first time we asked for this probability, we wanted the probability being less than or equal to 4, and which includes all the area below the curve there. And now we have just this probability in the green down there. So the probability should be doing what here? Should be getting bigger or smaller? Should be getting smaller, right? So when our variance is smaller, the distribution kind of becomes more squished in, so the probability of being kind of far away from the mean is should be getting smaller. Let's check that does indeed work out here. So with 50 people, this is now the probability. Take x bar minus its mean, divide by standard deviation, square root of 0.5. Again, this is thanks to the CLT. This is about the probability that a standard normal is less than negative 1.41, which is, if you look that up in the table, that's 0.0793. Which is indeed less than the 0.1190 we found previously. This is the CLT. Okay? Is everybody okay with that? Yes, Matt.
Just a real quick question. Like, how do you know which standard deviation to use? I guess, like the last one we just used like the square root of the 440, but this one we like did it differently.
Okay, yeah. So how do you know which standard deviation to use? So here's this extra slide that I thought I had. So again, the CLT tells us that x bar is going to be approximately distributed as normal with mean mu and variance sigma squared over n, or standard deviation sigma over the square root of n, when I'm dealing with the sample mean.
Okay.
So again, t is approximately, if I'm looking at the sum, it's approximately normal with the mean is n times mu, and the variance is n times sigma squared.
Okay.
Or the standard deviation is the square root of n times sigma squared. So first you want to figure out, am I talking about the sum, which I'm calling t, or am I talking about the average? Just the regular old average there. And then that should tell you. So you'll need to figure out what sigma is. If I haven't told you what the variance of the individual observations is, maybe you'll have to calculate it like we just did with the exponential distribution. But then, depending on whether you're talking about x bar or t, you either divide by n or multiply by n.
Makes sense.
Yeah.
So, like, is it correct to think about it as when you're increasing from 35 to 50, like the 15 you're adding, and essentially like expected value is 5. So that's why you're kind of like shifting it up closer to the mean. Is that? That's how I thought about it. That's why I thought it was decreasing. But is that?
Okay.
Think about it?
Right. So the question was, is it correct to think about if, as we go from a sample size of 35 up to 50, is the probability getting less because we're somehow shifting the adding onto the mean? Is that what you said?
Like increasing.
Increasing. Okay. So what we saw before was that the expected value of x bar equals mu. So it doesn't matter how many people I'm taking the mean of. I could be taking the average of 10,000 people. If I'm looking at the sample mean, where that distribution is centered will always be exactly the same. So let me draw that picture.
Where it's centered. I'm not really saying it's
Oh.
changing, but I'm saying that
You're pushing up the middle of it.
Yeah.
Oh, okay. Yes, absolutely. Yeah. Sorry, I misunderstood you. Yes. So let me redraw that picture. So if this is my sample mean x bar, here's the mean. It's centered at 4, so it's going to be approximately this normal shape here. Sorry, it's centered at 5. So this is for when n equals 35, for example. But then, yeah, again, when we add observations, we shrink down the variance, which means it's getting more squished in here. So draw this a little more clearly. So the distribution becomes something like this. And so if you're looking at the probability of being outside 4, for example, something like that, less than 4, that's exactly the right way to think about it. The distribution's getting kind of bunched up, more peaked in the middle there, so the area outside in the tail will be smaller.
So like the variance is decreasing because like as n is increasing, like the expected value becomes closer and closer.
Exactly right. Yep. So as the variance gets smaller, the mean will sort of have less and less variability. It'll get closer and closer to the expected value. Yep. So if I wanted to know the probability of being something like between 4 and 6, so if I'm looking at the probability of being in the middle, as my sample size gets bigger, that probability will get bigger. So it got smaller in the previous example because we were looking at a probability of being less than 4, something away from the mean. But if I look at the probability of being close to the mean, that probability will get larger. good question. Yeah. Does that answer your question?
Yeah.
Okay. All right. Well, I'll come back and do one more example of this later, just to kind of reiterate this. But for now, we're ready to move on to section 5.5. So it's kind of closely related to what we've just been talking about, but slight extension here. Okay. So again, section 5.5 here, we're talking about the distribution of a linear combination. So a linear combination is this thing right here. It's just some weighted sum. So I'm taking constants and I'm adding up. I'm weighting each one of my observations. I'm adding them all up. That's what I mean by a linear combination. So that's the definition there. So if I have n random variables, x1 to xn, and a bunch of numbers, constants, a1, a2, all the way up to an, then this is my linear combination. And that in general, just note that the random variables do not have to be independent and identically distributed. Doesn't have to be the case. It might often be the case, but linear combinations is defined regardless. So I'm just scaling each one of my x's and then adding them all up. That's what I mean by a linear combination. So for example, I've skipped over, I must have deleted a slide here. So for example, if I take y equal to 8, this is what I have written in your notes, 8x1 plus 3x2 minus x3, that's going to be a linear combination, right? Because I have x1, x2, x3. A1 here is 8. A2 here is 3. And A3 is -1. So just pointing out, that's sort of a simple example. So we're just multiplying each of our random variables by different numbers and then adding them all up. Okay, so similar to what we have sort of seen before, if each one of my random variables x1, x2 up to xn has mean values of mu1, mu2 up to mu n, so they don't all have to be the same. And the variances could also all be different, so sigma 1 squared plus sigma 2 squared and so on up to sigma squared n. Then regardless of whether these things are independent or not, their expected value I can calculate like this. So here's my linear combination. I'm taking the expected value of that, and I can distribute. This is just like what we've seen before, that the expected value of x plus y equals the expected value of x plus the expected value of y. So if I'm taking the expected value of a sum, I can just split that up and take the expected value of each piece, and also take the constant outside. That's something that we've seen before too, right? The expected value of a times x is just a times the expected value of x. That should be familiar from a long time ago now. And so this is true regardless of whether or not the xi's are independent. Okay. Looking at the variance of these things, so now I'm taking the variance of my linear combination. Now for this thing to hold, I do need them to be independent. So the same setup, I have these different random variables with different means and variances. But now I need them to be independent for this thing to be true. So for example, the variance of x plus y is equal to the variance of x plus the variance of y only if x is and y are independent. So that I can distribute the variance through the sum only if I have independent random variables. So I can split up the sums if they're independent, and then again, the other thing that you should remember is that the variance of a times x is a squared times the variance of x. So I can pull that constant outside, but I need to square it in order to do that. Okay, and then the standard deviation there is just the square root of what we just found there, square root of the variance. Okay. So let's look at, well, I guess I don't have this in your notes. You might be wondering, what about the variance of this thing if they're not independent and it's something that's slightly different? We won't ever use this, so I won't spend a lot of time talking about it. But it is still possible to find the variance of that sum. You just have to do some extra work. Okay, example here. We're going to go back to our gas station examples. We're going to say that this gas station sells 3 kinds of gasoline: regular, extra, and super. And they have different prices, so $3, $3.20, $3.40 per gallon. And let's let X1, X2, and X3 denote the amounts of these each of the fuel grades that are purchased on a particular day. And we're going to say that these things are independent, so the amount of each type of fuel that people purchase is independent of the others. The mean of the first type of gasoline is 1,000. The mean of the second type is 500. And the mean of the third type is 300. And then their standard deviations are there as well, 100, 80, and 50. And then the revenue, of course, we get $3 per gallon of the regular, $3.20 per gallon of the extra, and $3.40 per gallon of the super. So we're going to find the expected value and the variance of y, which is the revenue that we get here. So y equals the revenue, which is 3 times the number of gallons we sell the first type, plus 3.2 times second type, plus 3.4 times the third type. Okay. So let's here we go. We want the expected value and variance of y. So the expected value of y, that's the expected value of 3x1 plus 3.2x2 plus 3.4x3. And of course now I can just split these up and take the constant outside. So this is 3 times the expected value of x1 plus 3.2 times the expected value of x2 plus 3.4 the expected value of x3. And then I told you what all the means were. They were 1,000. Mean of the second one was 500. The mean of the third one was just 300. So that should give you an expected revenue of $5,620. Okay. And let's also quick find the variance of this thing. The variance of y, well, that's the variance of 3x1 plus 3.2x2. And we can, since they're independent, so because we have independence, I can split this apart. This is going to be 3 squared times the variance of x1 plus 3.2 squared times the variance of x2, 3.4 times the variance of x3. And the variances I gave them to you were, or I told you the standard deviations, I guess, were 100, 80, and 50. So if you plug all those in and square them for the variances, that'll give you 184,436. So the variance of x1 is 100 squared, the variance of x2 is 50 squared, and the variance of x3 is variance of x2 is 80 squared, variance of x3 is 50 squared. Okay. Pretty straightforward, yeah? Okay. So two more definitions, then we'll finish up with an example here. So sort of a special case of corollary, a special case of the result that we saw before, is if I want to know something about the difference. So I want to know the difference of two random variables. Well, that's just the difference of their expected values. But then, as long as they're independent, the variance of the difference is actually the sum of their variances. So this is, you can let A1 equal 1 and A2 equal -1, and then that result should fall out from, so let n equal 2, and then that result will fall out from the proposition that we saw just above the example there. Okay, so that's kind of interesting that if you want the expected value of this difference, you can just subtract the expected values. But if you want the variance of it, you actually have to add them together. You can't somehow take the difference of the variance. Yeah. Okay. One more proposition for you here. So now if I go back to the normal case, where if all these things are normally distributed, sort of this is our default situation here. So these things are all independent, but now they don't have to be identically distributed. They could have possibly different means or variances. Then any linear combination of these x's is also going to have a normal distribution. So this was, if our y is our sum from I equals 1 to n of ai times xi, this thing is going to have a normal distribution as well. And then the mean you can find, the mean will be equal to, again, I'm just adding up the AIs times the mu's, the mu i's, so maybe the mu's are all different. And the variance will be since they're independent, I can add this up. AI squared times sigma I squared. I now realize I've been throwing this around. Is everybody okay with the summation notation there? Is that something you guys have seen before? Okay. That's going to be a nice shorthand for us to use. That just means I'm summing over all the subscript. I'm summing over the subscript I there. So from I equals 1 up to n, I'm adding up all those things. Okay. One more example. We'll practice using this thing. So now we're looking at automobiles again. We have 5 cars that are all the same type are going to be driven on a particular trip. And so the first 2 are going to use an economy brand of gasoline, and the other 3 will use a name brand of gasoline. So let's let x1, x2 up to x5 be the observed fuel efficiencies. So I'm going to take this trip and figure out what the fuel economy is for each one of these vehicles for the 5 cars. And we're going to suppose these things are independent and have a normal distribution. The mean of the cars that are using the economy brand is 20 miles per gallon. The mean of the name brand type of gasoline is 21 miles per gallon. And then I have slightly different variances there. So sigma squared is 4 for the economy brand and 3.5 for the name brand. And we're going to define this random variable y as follows. So x1 plus x2 over 2, and then subtract off x3 plus x4 plus x5 over 3. So what is y looking at here? What is when I calculate y, what will that tell me? I'm thinking about comparing the fuel economies of these 2 types of gasoline. Which one's more efficient? Exactly. So, yes. So this will tell me which one's more efficient because here I have the average of the economy brand, and here I have the average of the name brand. So that's not a necessary part of the example, but just to kind of note that that's what we're talking about. Okay, so a question we can ask now, what is the probability that y is less than 2? Okay, so we know. Again, we're told here that these x's have normal distributions. So they're independent. They have normal distributions. So that means y is also going to have this is going to be distributed as a normal random variable as well. And to answer a probability question about it, we just have to figure out what the mean and variance are, right? So the expected value of y is just going to be the weighted sum of the means. So this is going to be 1/2 times mu1 plus mu2, and then subtract off the mean of the other three. So mu3 plus mu4 plus mu5. So maybe I'll just note that a1 is the same as a2 is 1/2, and a3 is the same as all the next three, which is 1/3. So those are my weights here in this case. Okay, so mu1 and mu2 are both 20. Mu3, mu4, and mu5 are all 21. So this is just 21 minus. Sorry, I'll write it out here. 1/2 times 20 plus 20 minus 1/3. And that will give me -1. Okay, and the variance of y is going to be, I can split apart that sum and add up all the variances weighted by the squared weights there. So this is going to be 1/2 squared times sigma 1 squared plus 1/2 squared. So those are my, sigma 2. Then 1/3 squared times sigma 3. Same for all of these. Sigma 1 and sigma 2 are 4. Sigma 3, sigma squared 3, 4, and 5 are all 3.5. So if you calculate that out, that will give you 3.167. Okay, and so that tells me that now y is going to have a normal distribution with mean -1 and variance 3.167. Okay, so I have a normal distribution, so I don't need to worry about central limit theorem or anything like that. I can now answer a probability question. So I want the probability that y that the difference here is less than 2. So I can just do the usual standardizing trick, y minus -1 divided by the square root of its variance, square root of 3.167. And that's probably that a standard normal is less than 1.69, which is 0.9545. This is okay. I'm out of time. Thank you guys so much for being here. Have a great weekend, and make sure to get your homework in. We'll collect that at the beginning of class on Monday. Have a good one. How's it going, Andrew? It would only happen when you're wearing white shirt.